Vacuum tubes, or valves as the Brits call them, are fairly commonplace for us audio engineers. However, ask around outside the audio world and you'll find that most people know nothing about them, other than that they're old. Hell, I got a bachelor's degree in electrical engineering and they were hardly even mentioned in the curriculum outside occasional history of electronics lessons. The information age and modern technologies we know has all been about transistors, but it was tubes that really kicked off the technological revolutions of the 20th century in computing and communications. Despite being significantly outperformed by transistors, tubes have somehow managed to stick around in a few niche applications, mainly audio. In this video, I want to talk about why vacuum tubes are still so prevalent in the audio industry despite being an invention that's over 100 years old with alternatives that are smaller, cheaper, safer, more efficient, and have a longer operating life. There's a pretty simple answer, and we've all heard it, because they sound good. But we're engineers, and we want to know why they sound good. To understand this, we need to take a look at how the tube works in the first place. Believe it or not, a great starting point is the light bulb. Incandescent light bulbs consist of a filament in a vacuum-sealed glass envelope. When connecting a voltage source across the filament, current flows through it, heating it up to such high temperatures that the filament begins to glow. In 1880, Thomas Edison noticed that over the lifetime of the bulb, there would be a darkening discoloration on the glass, but only on one side. This was due to a phenomenon called thermionic emission. As you heat up any material, what's really happening is you're adding energy to the atoms. When this happens, it's the electrons that are absorbing that energy. Now, in the interest of time, I won't dive into the physics of electron energy levels, but in short, when you give electrons enough energy, they can escape the atom and become a free electron. Basically, when you heat up a metal enough, it starts spitting out electrons. And because those electrons are negatively charged, they are attractive to the positive end of the wire, most of which end up zipping past the wire, hitting the glass, discoloring it over time. Now keep in mind, electrons weren't even discovered until 1897, so Edison wasn't exactly sure what was coming off the filament. He attempted to resolve the issue by putting a plate in the bulb to catch the emissions. It didn't turn out to do too much on its own, but in experimenting he found that if you put a battery between the filament and the plate, current would flow if the plate had a positive charge, and no current would flow if the plate had a negative charge. The phenomenon was dubbed the Edison effect, but unfortunately for Edison, he didn't see the value in it and only patented it as a simple voltmeter. In 1904, while working on developing early radio receivers, British scientist and former advisor to Thomas Edison, John Ambrose Fleming, needed to find a better way to perform rectification of radio waves to demodulate the AM signal. Rectification is the act of converting AC signal to DC, while the other components such as capacitors are needed to smooth out the signal and provide a flat DC signal. The simple rectifier at least gets all of the signal to be positive. Fleming remembered back to the Edison effect and created the first thermionic valve, otherwise known as the diode, di for two, ode for path. A diode is an electrical device which only allows current to flow in one direction. When the plate is positively charged, electrons emitted by the filament would be attracted by that positive charge, and they would flow to the plate, aka current flow through a vacuum. If the plate had a negative charge, it would actually repel free electrons, and there would be no current flowing. Note that the plate is referred to as the anode, or positive electrode, and the filament is referred to as the cathode, or negative electrode. Diode tubes are mostly used in audio as a form of rectifier tubes to provide high DC voltage to the other tubes of the circuit. Here are some of the most popular rectifier tubes in audio gear. While they may not have a very strong impact on the tone of the gear, the power they supply can influence the performance of the tubes downstream. In a guitar amplifier, it can affect the feel of the amp, depending on the speed of the AC to DC conversion and the speed of recovery under spikes in the input. Here's a more realistic diagram of a vacuum tube diode. Most tubes use this cylindrical construction rather than the previous diagram's more simple light bulb-esque depiction. Also note here that the cathode is not the filament itself, but a plate, usually made of nickel and coated with metal oxides, that's being heated by a heater element, which is usually tungsten filament. This is called an indirectly heated cathode and is much more common but still works the same way as directly heated. The Fleming diode was great, but it could only be used for rectification. When we think of tubes in the audio world, we're usually talking about amplification. That didn't come out until 1906 when Lee DeForest added a third connection, a wire bent into a zigzag shape called the grid, that was placed in between the filament and the plate. This was dubbed the triode. The grid allowed for control over the flow of electrons on the plate, similar to how shutters on a window control the flow of light into a room, or how the handle on a water faucet controls flow of water. Applying a weak positive voltage to the grid with respect to the cathode will increase the total attraction of electrons in the direction of the plate, increasing the current, whereas adding a weak negative charge to the grid with respect to the cathode will decrease the total attraction of electrons in the direction of the plate, decreasing the current. Therefore, small changes in the grid voltage can create large changes in the current coming off the plate. This allows us to connect our input signal to the control grid and essentially replicate the waveform at a higher magnitude. Triodes are commonly used as preamplifiers. The most popular by far is the 12A something 7 family, like the 12AX7, 12AT7, 12AU7, and 12AY7. The difference between all of these is simply their gain. You may also see them noted as ECC81, 2, or 3. These are electrically identical to the 12A7 tubes, but ECC is just the European model number. The most common you'll likely see is the 12AX7 dual triode preamp. This can be found in practically every guitar amp brand you can think of. Mic pre's such as the LA610, the Manley Voxbox, and tons of outboard gear like the classic Pultec EQ and LA2A opto compressor. Triodes were great for amplification, but still had some problems. In a triode, there are capacitances between the grid and the anode that can cause feedback or resonant oscillations at really high frequencies. In an effort to alleviate that, the next evolution in tube architecture came about in 1926 when another connection was added. The tetrode, tetra meaning 4, introduced another grid to the tube. The screen grid was placed between the control grid and the anode, and the screen grid was typically kept at a constant positive DC voltage. What the screen grid does is eliminate the control grid plate capacitance and therefore stabilize oscillations, greatly improving the high-frequency performance of the triode. The tetrode also had a major drawback, however, with something called secondary emission. This was when an electron strikes the plate with enough energy to ionize the plate itself, causing it to also emit some electrons. In a triode, the electrons are simply recaptured by the plate, but in the tetrode, they can be attracted to the screen, thus decreasing the output current. This is very clearly observed if you take a look at the IV curve or plot of the anode voltage versus anode current at different grid voltages. As you can see, there's a large dip in the curves, which is referred to as the tetrode kink. Because of this, normal tetrode tubes are not often used in audio, and there are some alternatives that we're going to talk about now. In 1929, this issue was solved by, you guessed it, adding another grid. The Pentode introduced a third grid and fifth electrical connection between the screen grid and the anode. This new grid was called the suppressor grid, typically wired directly to the cathode or ground. The job of the suppressor grid was to repel any electrons that were the result of secondary emission back at the anode. Essentially, the Pentode gave all the benefits of a tetrode while removing the kink in the IV curve. While Pentodes can be used as preamplifiers, most are commonly used as power amplifiers, with the most famous being the EL34 and its lower-powered little brother, the EL84. These are extremely common to see at the output stage of guitar amps. EL34s are typically seen in many British high-watt amps like Marshall, Orange, and high-watt brand amplifiers, and EL84s are typically seen in lower-watt Class A amplifiers like the Vox and newer Fender amps, as well as the low-watt versions of previous mentioned brands. Philips Mollard held the patent for the suppressor grid of the Pentode valve, which forced competitors in the market to find other solutions for the tetrode kink. In 1932, engineers at EMI solved the issue by making use of geometry and using plates to focus the electron beam into a small area of the anode, minimizing secondary emissions. This was called the beam tetrode, or kinkless tetrode, KT for short. Beam tetrodes, like Pentodes, are commonly used as power amplifiers, with the most famous being the KT66 and 6L6. The KT66 has a slightly larger heater current and has been noted as having a fuller low end than the 6L6. However, both are known for their very clean and bright sound, with less distortion than their Pentode EL cousins. 6L6 tubes are much more common to find, and they were used in all of the classic Fender amps, like the Twin Reverb, and interestingly enough, the Mesa Boogie dual rectifier amp. Okay, so now we understand how each of these tubes work and how they can amplify a signal, and a little bit how they're used, but we still don't know why they sound the way they do. The tube is essentially a voltage-controlled current source. A voltage at the input, the control grid, controls the flow of current to the output. Let's take a look at a graph plotting how the plate voltage and current relate to grid voltage. For this example, we're going to be looking at the 12AX7 dual triode tube. This is called the plate characteristic graph. On the x-axis, we have the plate voltage, and on the y-axis, we have plate current in milliamps. The multiple different lines represent the different grid voltage that you may be operating at. Now, this is a very useful chart that can tell us all about the performance of a tube and help make design decisions for the circuits in order to get the tube to operate in very specific manners. In the interest of time, I won't get into all the details of all the different things this graph can tell us about the tube. But the big takeaway is that looking at the different grid voltage lines, you'll notice that they're not only curved, but they're curved at different rates for different grid voltages. Also note that the grid voltage lines are much more bunched up on the right side of the graph versus the left. We'll explain why that's really important in a minute. But all of this means that as the grid voltage changes, or as the input signal changes, the output will not track perfectly linearly. That is, the output waveform will not be a perfect copy of the input waveform, simply scaled up from the amplification factor. The amplification of a vacuum tube is non-linear. Different input voltages will be amplified at different rates. In essence, the tube changes the shape of the wave, distorting the waveform. Depending on how the circuit is designed, there can be more or less distortion, and all tubes have a slightly different plate characteristics. But nonetheless, vacuum tubes in general exhibit non-linear amplification. That's the key detail. The result of the distortion caused by nonlinear amplification is new frequencies will become present in the sound due to the changing waveform. More precisely, harmonics are created. Harmonics are whole number multiples of the fundamental frequency, where the first harmonic is the fundamental itself, second is double the frequency, third is 3 times the frequency, and so on. Second, or even order harmonics refer to the even multiples of those fundamentals, like second, fourth, sixth, eighth, and so on. Third order, or odd order harmonics refer to the odd number multiples of the fundamental, like third, fifth, and seventh. The type of harmonic distortion given by an amplifier depends on whether or not the amplification is symmetrical or asymmetrical. Asymmetrical gain produces more even order harmonics, which contain the second, fourth, and eighth harmonics. Note that these are all doubles of each other, and therefore they're actually musical octaves, which is why even order harmonics are generally considered to be more pleasing to the ear. Odd order harmonics, especially higher order ones, don't align well in a musical sense and can have characteristics that can be described as dissonant or tinny, but that doesn't mean they can't sound good. It's all about balance and the magnitude of these harmonics being added. Remember back on the 12AX7 plate characteristic chart, we noticed that the grid voltage lines were more bunched on the right side of the graph. This was showing that the tube demonstrates asymmetrical gain. At more negative grid voltages, there is less gain, therefore the tubes primarily create even order harmonics, thus resulting in a more musical and pleasing sound that we enjoy. It's important to note that almost all tube-driven circuits require an output transformer, because tubes have a very high voltage and very low current, therefore a high output impedance. And most devices following an amplifier, like a speaker, expect high current, low voltage, and low resistance. The transformer being used itself also colors the sound from its own transfer characteristics, and is going to play a significant role in the sound of the gear. The sound of a piece of gear is almost never simply the product of a preamp tube or power tube or the transformer alone, but the product of the entire circuit and all of the components within it. Okay, that was a lot, sorry. But in reality, it's only scratching the surface of discussing the role of vacuum tubes in the audio industry. And I hope this video has given a good baseline knowledge of how a tube operates, the types of tubes, and how they can affect the audio we pass through them. If you're interested in learning more, please let me know and I'd be happy to discuss further and share some resources that can help. Thanks for watching.